So let's go back to where we stopped. We had this this least squares problem, right? Which, well, we have a function that we want to minimize over all vectors beta. So now I'm describing the problem in a slightly different way, right? We have some function of beta that we want to minimize, which is an expectation. We don't know how to compute the expectation, so we replace the expectation by this sort of empirical version, as people like to say, an empirical measure, right? So we're taking an average over the sample, over the data points. And so we wanted to minimize this function. We minimize this function instead. And we want to know how much worse we do when we do that. Right? So this would be the theoretical minimum, and this is the minimum we achieve by our method. Right? So this is part of a very broad class of problems. Let me maybe write the name here, which is called empirical risk minimization. It's hugely important because this idea of replacing minimizing expectation by minimizing empirical risk is very widespread. It appears all over the place. And so there are many people whose research is essentially devoted to understanding what empirical risk minimization works. What it does when the different sorts of assumptions. And but here we're in a case which is in some sense very simple, which is this least squares case. But it turns out that many of the features we find here also appear whenever this function L here is strongly convex. And what strongly convex means doesn't matter too much for us. Well, and but here we have a very special structure. What we showed over here is that we had this matrix sigma, which is its expected value. We showed that we can express this difference in losses by this. I'm just going to put this over here. This is the same as this quantity here. We still don't know anything about what this looks like. But we know that if we can bound this thing, then we can bound this other thing. Right? They're the same. I mean, there's not just a matter of bounds. They're exactly the same. Right, so what we're going to do now is to try and figure out what this looks like, at least in the sense that understanding where does this random matrix that we defined, we're going to try to see where it comes in, where properties of it actually matter for the kind of calculation we're doing. And now the linear algebra gets a little bit more complicated than before, so please ask questions, stop me, and if anything looks weird. So what do we know about this beta hat, right? So we want to bound this norm, but we don't know much about beta hat, right? We only know one thing. We know that, well, let's define this sort of empirical loss function. And essentially the only thing that we know about this vector beta hat here is that its empirical loss is less than the empirical loss of any other vector, because that's how we define it, right? So that's the definition over here. Okay, what about this? Well, in particular, I can take this vector here to be I can take this vector here to be the beta min. And now let's do something with this thing here, and we're going to see where this leads us, right? We're going to analyze this inequality here. Right, so let me just make things slightly simpler and make them look like what we had before. I'm going to define epsilon I to be equal to yi minus xi in a product b min. And remember, well, I had the original epsilon was y minus x prime beta min. So those epsilon i's are IID copies of this random variable here. And okay. So, and now it's very easy to see that if you take the empirical loss of beta min, you get a sum of these guys squared. I'm just saying this. You get the average of these guys squared. Right? So what about this other? Well, okay, so this should be beta hat, right? So what about the other side? I'm more or less repeating the calculation I did with this L function for the L hat in. Okay. So L hat of beta hat n is just the sum and yi minus x inner product b hat n. Now, this thing over here, you can rewrite it as epsilon I plus x inner product with b min. I'm going to use this here. And because I have x in the product b min minus x in the product b hat, I can just write it like this, right? Now, what am I going to do with this? I'm going to expand the square, which is all I can do, really. Right? So first I'm going to get the sum of the epsilon I squared, which is just the empirical loss of beta min. Then I get the sum here. And now I get a third term, which is a cross term. Right? Is everything okay? So what do I know here? I know that the empirical loss of beta hat is less than the empirical loss of beta min, which is this term. Right? What this tells me is that the sum of these two terms must be less than or equal to 0. Right? Again, I'm saying that this minus this is less than or equal to 0, which means that the sum of these two terms is less than or equal to 0. So, and right, okay, there's a beta min here. Yeah, let me just try to, well, it doesn't matter too much, but let me. This is less than or equal to 0. But now I want to write it in a slightly different way, which is just to say, well, this sum is less than or equal to 0. It's because this must be true. Right? Okay, so now we need to recognize, first of all, that we have a matrix sigma hat in there. And it's not hard to see what it is. But where is it? Well, maybe it is hard to see what it is, so maybe I shouldn't. I mean, if you remember the previous calculation, where we look at this difference, the matrix sigma appeared, it showed up in the quadratic term. Right? And the sigma hat appears here in the quadratic term as well. Let's look at this. So we have 1 over n and let me just, well, maybe I should even, I mean, I even wrote this before, right? So if you have, that's one of the very first calculations I did. You have this sort of sum. It equals v hat sigma hat, v inner product sigma hat v. So here I have this with beta min minus beta n. So maybe I should have kept this first term. Is 1 over n. Oh, sorry. And as we argued before, we said that sigma is positive semi-definite. The same is true of sigma n, right? Precisely because we know that this expression, if you take v inner product sigma hat v, it's always going to be a sum of squares. So it's always no negative. And it's symmetric. So this is going to be, this is the same as sigma hat n 1/2 here. Now the second term, I'm going to write it as in a slightly different form. Which is the following. It's, I want to have something around here that looks like this. Except that for reasons that will become clear later, I don't want to have sigma hat in here. I want to have sigma. So, so what I'm going to do is, well, there's lots of things I want to do. So maybe I'm going to do them one at a time. Well, the first one I'm going to do is really simple. Here I have a sum of inner products, right? And that's the same thing as the inner product of the sums, because the inner product is linear. So then there's not much going on here. Now, as I said, I want a sigma 1/2 to appear over here. What do I need to do for that? Well, I need to multiply by the inverse over here. Is that clear? Because I want the sigma hat to cancel the sigma minus 1/2 in the inner product. So here, because of the way I'm doing things, I could be a little bit more careful, but I'm assuming this matrix is invertible. If you wanted something a bit more general, then you can say, well, even when a matrix doesn't have an inverse, if it's symmetric, it has a pseudo-inverse. There's an operator such that when you multiply sigma 1/2 by it, it gives you the projection onto the span of sigma, and that would be enough. But let me assume that it's invertible because it makes life a little bit easier. So is it clear that these two things are the same? And just using the fact that, well, if the inner product of A and B equals the inner product of A times M, M minus 1, and B, which is the same as inner product minus 1A, and B if M is symmetric. Because we know that symmetric matrices have symmetric inverses, so you can move them from one side to the other of the inner product without changing the matrix. Right? So this is what I have over here. So let me go back. And so now we have this expression saying that, well, this norm is less than this inner product. And I'm going to apply Cauchy-Schwarz here. And they're going to get something that it's almost good. It's going to see. Right, so so now our current status is this. This is less than minus 2 over n epsilon I minus a hat xi, inner product of that with sigma 1/2 beta min minus beta. Now I can apply Cauchy-Schwarz and get the norms here. And then you get, well, the norm of vector 2 over n times the norm of this guy and you can see that you have something that's almost an upper bound on this expression in the following sense. Let's pretend that we can replace this sigma hat, right? But let's pretend we can replace this by sigma. Then you're saying that sigma hat applied to this vector is less than something times sigma hat applied to this vector. So let me write it like, if we have this exactly, we don't have this exactly, of course. But if we had this, and then this would be the same as this term. So you get something like and why is this good? Because as we pointed out before, I mean, now I just erased the formula, but this is the excess loss of beta hat, right? This is how much, so we know that beta min has minimal loss. How much more does beta hat lose? This is this expression. So now we're saying we can bound this loss, and I mean, I argued that it was sort of a complicated object because beta hat depends on the random variables, but now you have something which, well, it sort of looks funny, but it is a sum of independent random vectors here. Because what are the vectors here? The vectors here are the following. So this is also between quotes because it's not quite right. So defining Zi to be equal to epsilon I sigma minus 1/2 xi, we've just seen that the loss, okay, this is still, everything's between quotes because we're making this assumption which you know is not true in general. So we have to fix that later. And we even know that the mean of Zi is 0. Okay, these are IID. And we know that the mean is 0 because the mean of epsilon I xi equals 0. Why do we know that? Because remember that we knew that the mean of epsilon times x equals 0. And epsilon I times xi is just an IID copy of that. So you have a vector with mean 0. Here we're sort of implicitly using another linear algebra fact, which is that, okay, zi is sigma minus 1/2 times epsilon I xi. This is just because, well, this is a scalar, right? So you can pull it outside of the multiplication. Now if you take the mean, you're taking the mean of a linear transformation of a vector. And that's the same as taking the mean first and then doing the linear transformation. Well, why is it true? Then you have to, it's the same sort of calculation that we did before, right? You have to write this down in coordinate form. And, well, maybe you look at the first coordinate of this. What does it look like? Well, and then you see that this works. So it's not obvious, but it's true. And, well, of course, again, this is between quotes because there's something that we assumed here which we shouldn't assume. But if we just pretend this is true for the moment, we managed to reduce this least squares problem, which had some sort of weird dependencies, to a problem about sums of IID random vectors. And this, I mean, I'm not going to say why right now, but we're going to see a bit later, maybe, I don't know, that this is something like we expect this to behave like the ratio of the dimension to n. Right? Why? Because zi, the expected norm of zi squared, it's something like a noise term times the dimension, or expected to be like this. And then, well, just like if you take, okay, so maybe this, if you take a sum of mean 0 vectors like this and compute the norm squared, take the expectation, that's the same thing as the sum of the expectations of the vector squared. So, okay, what did I just say? It's an exercise. Is that the expectation of the sum, I mean, the vector is IID with mean 0 here, that's all that matters. So this is, oh, I mean, actually I just need independent with mean 0. Something like this. And then we expect the norm of this vector to be more or less the dimension. So that's what we expect the loss to look like. And this you can show that is optimal. I mean, here we just proved an upper bound. Well, actually I haven't proved anything because I'm assuming this. But what we're going to do is prove an upper bound. And then it's a bit more complicated to show that you have a lower bound of the same order, given the kind of condition we're going to discuss now. Well, this is all in the references for the course. So you can also look it up there. Right, so this gives us something, except that we assumed something we know to be wrong, right? But now I'm gonna sort of fix this computation by assuming a condition that's this kind of theorem we want to prove about this. Right? I mean, it should be clear that somehow if this matrix is very close to this one, then this calculation should be okay, more or less, right? Because after all, I'm just, okay, if this is not exactly the same as this, but it's sort of similar, then we're good. So let me write down something here, which may or may not be true, which is this, that an assumption that you can make that v hat sigma n, v is less than some alpha times v hat sigma v. Here alpha is some fixed number greater than 1. and this is for all v. Do we expect this to be true? There are two possible answers. One is yes, and the other one is no. So, I mean, in the limit when n goes to infinity, is this going to be true? Different question. What does this converge to when n goes to infinity? No. It converges to sigma, right? So what we have in the limit is that v inner product sigma v is less than alpha times v inner product sigma v. Since alpha is greater than 1, this is of course true. So we expect this to be true in some sense. And I mean, you can see that you expect even more to be true, right? We expect this. I mean, here there's something that you need to take care of, which is, you know, I mean, this expression here, it's not going to go to 0 uniformly with v, just because we're considering all possible vectors here. So you can take a vector of norm million or any size of norm n, and this is not going to go to 0. So you need to divide by something. So it turns out that it suffices to divide by this, assuming that sigma is invertible. So this goes to 0. So this is telling you something uniform, and this is uniform in V. And this is almost surely, right? Oh, okay, so the actual statement is that this so not only you expect this to be true, but you also expect this expression to be lower bounded by something, which would be like 1 over alpha times v inner product sigma v. But what I'm going to do only requires this upper bound here. And, sorry, no, I mean, it only requires this lower bound, and then I have to change everything. The alpha should move here. Right, so I'm saying that in the limit, this is equal to this. So I'm multiplying by something that's slightly larger than 1. Because this convergence is uniform here, I expect this to be true for all large enough n with high probability. Right, so what does this give me here? I can come back here. I can see that 1 and the star condition, they're going to give me the following. So now I can lower bound this. And why can I lower bound this? I mean, another way of saying this, okay, so let me write down this star condition. It implies that sigma hat n 1/2 v squared times alpha is greater than sigma 1/2 v squared for all v. Is that true? I mean, I just wrote the same thing, right? Because this norm here is exactly this, and this norm here is exactly this. Okay? And now you combine these two things, and you're going to get that, well, I have a lower bound for this, which is, well, sigma 1/2 beta min minus beta hat n is less than alpha times sigma n hat 1/2 beta min minus beta hat n, which is less than this thing here. Well, alpha times this thing here. now let's look at what we have. Now we have something that we like, right? So we have this quantity, exactly the same quantity here. The only thing that is different from what we had before is that there's an extra factor of alpha there. So, and then you just need to redo the calculations. We can conclude that if this holds, then, well, the excess loss, which is equal to this norm difference here, this norm here, is less than or equal to, well, you're going to divide by this, right? So you get that this is less than alpha times this norm. So then you have to square again. And you'll get this creature here, which is again, well, with alpha as a constant, this is again of the order p divided by n. So it turns out that we don't need put it like this. Here we did a calculation assuming that sigma hat n is equal to sigma. We don't actually need that if we just want an upper bound. We just need something of this form. That sigma hat n is lower bounded by sigma. And if we want everything that we just wrote to be true with high probability, then we just need this star condition to be true with high probability. Right? And there's a thing that turns out to be very nice about this condition here. As you're going to see, the fact that it's one-sided. Right? I'm not asking for an upper bound for this. I'm just asking for a lower bound. And it turns out that getting these lower bounds is much easier than getting upper bounds here. You can actually prove that the conditions for having such a lower bound are much, much less demanding than the conditions for having an upper bound. Right, so now we sort of know why this sort of question is important, right? So we want to prove that sigma hat n is similar to sigma. Well, I mean, again, for some applications, you need sigma hat n to be close to sigma on both sides. You need the upper and lower bounds. For this application, you just need the lower bound. Right? And we know that if we have such a lower bound, then we can prove a theorem about the performance of least squares, which is going to be something like this. And this is, I mean, it's debatable from how important this is from a kind of a practical perspective, because, you know, if you tell a statistician or someone in machine learning, here, I proved that ordinary least squares works, they're just going to laugh at you. I mean, they say, I've been using this for 30 years, and so has my PhD advisor and everybody else. I mean, why do I care? It works, obviously. Look at the data. I won $3 billion just using this estimator. Right? But from a theoretical perspective, it's, you know, it's surprisingly difficult to get a sharp analysis of this thing. So this is an interesting result in that sense. We're trying to understand something that people do on a daily basis and for which the theory is still sort of lacking. Right, so this sort of finishes the introduction. So we have these two examples of random matrices. I mean, again, the examples are, well, the second example was this random covariance-type matrices that we just discussed and used for least squares. And the first example were those symmetric entries with independent entries above the diagonal. So now we're going to start talking about the proof techniques that we need in order to understand the two examples. And we're going to start with the Wigner matrices, the matrices with independent entries. And actually, we're going to do something very simple. And unfortunately, I didn't finish writing all the notes on time. I mean, I know the proof, so you don't need to worry about that. But I think I'm gonna have time to go through the whole proof today. I wrote most of it down here, but I'll have to finish writing it up tomorrow or something, so they can have it complete. Right, so are there any questions about this before we move on? Right, so what we're going to do is this. We're going to take the simplest case of Wigner matrix, which is the case that Wigner himself studied in his paper. And I'm going to give you a rough idea of what the basic theorems about these matrices are. And then I'm going to prove a weaker result, which in some sense is nicer. Well, the proof is nicer because it's a more general proof. It applies to Wigner matrices, it applies with matrices or non-dependent entries, so it applies to a broader range of things. Right, so what is the context here? So you have this matrix whose entries are just IID random variables above the diagonal, above and on the diagonal. And you make it symmetric, right? And just the entries are going to be called Nij. So with this convention that if I flip I and j, I get the same random variable, right? Because I want a symmetric matrix. Right, so I mean, regardless of the values of Nij, because the matrix is symmetric, we know that the spectrum of this matrix is contained in the real line. Right? That's just because the matrix is symmetric, you have a real spectrum. And you know that you have n eigenvalues with multiplicities. And you can ask questions, different kinds of questions about these eigenvalues. And Wigner had some very nice results about, well, his original results were, I don't think I actually wrote them down, but his original result was this. So let's say that you take a sum like this, where you take a function f, which is nice in some sense. Well, let's say C infinity with compact support. It doesn't need to be that smooth, but that helped. And you take the average of f of lambda over lambda in the spectrum, and you count the eigenvalues with multiplicities, right? Which means that if an eigenvalue has multiplicity 3, it appears 3 times in the sum. Counting repetitions, you want to have n terms in the sum. So what Wigner proved, this is really a weak convergence result. Well, I don't think he proved almost sure convergence. He proved convergence in probability, but these days we know that convergence is almost sure. He proved that this thing here, okay, so you need to normalize the matrix. So you need to divide by square root of n. And then you get this expression here, which is called the semicircle law. And here you have to multiply it by, I keep forgetting what the integral of this is. It's something related to pi, so maybe 4 over pi, I don't know. Okay. Whatever you need to have a probability distribution. So this is called the semicircle law because it's saying that, well, what you could call the spectral measure, the measure that puts mass on each eigenvalue equal to its multiplicity. This is telling you essentially that the spectral measure, which is a probability measure on the line, converges almost surely to this measure that has this semicircle density. I mean, this density that goes from -2 to 2 and has this shape here. This is a function 1 minus x squared over 4. Wait, there's that. Yeah, that's right. Yes, -2 you have 0, and then, yeah, exactly. So, unfortunately, this result, if you plot it like this, it suggests that the largest eigenvalue must be here, and the smallest eigenvalue must be here. That's not entirely obvious, because here I'm saying, well, that the number of eigenvalues fall, if you normalize like this, I'm saying that the number of eigenvalues falling outside of the interval -2, 2 must be very small compared to n. Right. But you can prove it's a different theorem, and you can prove this theorem, which is more like what we want to prove. So let's write down the eigenvalues of omega n in order. Right? So you can prove that lambda 1 of omega n divided by square root of n converges to -2, and almost surely. And the largest eigenvalue converges to 2. Right? I'm not going to prove exactly these results. I'm going to prove something weaker. I mean, this is certainly not even going to touch. And I'm going to prove something weaker than this, but with a proof that in some sense more robust, more general. And right, so what this tells you is that, the norm, you can conclude from this that the norm of omega n, the operator norm, if you divide it by square root of n, it converges to 2. Just because we know that the operator norm is the maximum of, well, it's the maximum absolute value of an eigenvalue. So the smallest eigenvalue converges to -2. The largest eigenvalue converges to 2. It means that essentially the eigenvalues are all contained in an interval -2 and 2, and you have eigenvalues that are arbitrarily close to the two extremes when n is large. So you get this limiting result. Right? So of course you can ask all sorts of questions. What if the entries are not normal? So it turns out, that these results can be extended to non-normal entries if the entries are still IID. So for instance, for this result here, which is the one we care about the most, this will hold if the entries have finite fourth moments. That's necessary and sufficient. And there's a book in the references by Greg Anderson, Alice Guionet, and Ofer Zeytouni that has a proof of that. Okay. So how is this proven? Well, let me give you an idea of how you could prove this directly. It's just a very rough idea because next week there will be a talk by Afonso Bandeira, and he'll use this same idea to find the spectral norms of other kinds of Wigner matrices. The main proof, the classical proof of this theorem is based on the so-called trace method. And the trace method works as follows. So let's say you want to know what the norm of a symmetric matrix A is, right? And let's say you want an upper bound, which is mostly what we care about here. So this norm, as we know, it's the maximum of the absolute value of lambda when lambda ranges over the spectrum of A. So here I'm assuming A is symmetric. Right? And this thing here is, of course, the maximum of lambda raised to 2 times k for lambda in the spectrum. A here. If you take the 1 over 2, the 2kth root, and here 1k to be an integer. So why is this? All I'm saying here is that, well, when you take the squares here, you don't care about the absolute values anymore, right? And you're taking even powers, so you don't care about the absolute values either. And then you're saying, well, if you take the maximum of these numbers raised to these powers, and they take the square, the roots, you get back these absolute values. So no big deal. But now you can do something which turns out is good. So you can take this sum here. And here again my sum is with multiplicity. So if I have an eigenvalue with multiplicity 3 or 5 or 7, it's going to show up 3 or 4 or 7 times, 3 or 5 or 7 times here in the sum. And what is this? This is just a trace of A raised to 2k. Right? The trace is a sum of the eigenvalues. Raising A to a power just raises all the eigenvalues to that power. So here we're just taking the trace of A raised to the power 2k. Right? So now how can you proceed from here? Well, if you take a Wigner matrix, it turns out that you can write down this trace more or less explicitly, as it's, the expectation of the trace, you can write down explicitly, and you can compute it. You can see that, well, even though the expansion of the trace has many, many terms, most of them will turn out to be 0, just because these entries have 0 mean. And then you can do some combinatorics, and after a lot of sweating and some effort, you get this 2 here. But you don't actually get a very good bound, for instance. We're going to see that for our applications, we'd like to have something like this. When a bound on what's the probability that this is greater than 2 times square root of n plus t. And we want this bound not only for n very large, but we want it for any value of n. Right? Because and this comes up very often. Remember that the motivation, the problem that I gave you as motivation for this was this problem about finding communities, right? And in some sense, what you need to make sure that you can find the communities, well, you end up having a very delicate relationship between P, the probability of connection inside a community, the probability of connection outside of the community, which is Q, and the size of the matrix. So you need, the real question would be something, for what values of N, P, and Q can you recover the community A and B? This is what you're going to hear about on Friday. And typically you want to consider an n that's very large, but you also want to consider a p and a q that go to 0, which is saying that, well, the number of people in the world perhaps is very large, but you typically have very few friends, right? And as it's going to become clear later on, this sort of bound is much more important than this convergence result over here. you need to be able to say something for n equals 1,000,000. What values of P and Q can I have in order to be able to find the communities with large probability? So you need what we call sometimes finite sample bounds. You need bounds for finite n, not just some limiting statements. And you can get bounds for finite n from such calculations, but they're messy, they're complicated, and the methods don't generalize very well to other problems. So let me show you a method that generalizes very, very well and can be applied to a lot of problems. And well, I guess that there's what I'm going to show is a very simple instance of something called chaining. But maybe the best way to do is in this case at least, is discretize and take union bound. And the method I'm going to show you is the following. So we're going to start from a different characterization of the norm, which is we know that the operator norm of this matrix, we even said that before, because it's symmetric, this is the maximum over V inner product WNV, where V belongs to the unit sphere. Right? I mean, again, that's only because the matrix is symmetric. Otherwise, you don't know that the operator norm is this. But anyway, since it is symmetric, then the proof is going to follow the following outline. So the first thing is you replace Sn minus 1 by some finite set. And 2, the probability that Wn is big, well, you replace by some finite set with the loss here. Well, as we're going to see later. So the probability that you get this norm is greater than lambda is less than the number of elements in your finite set times the probability that V inner product Wn V is greater than lambda over 2 or something like that. So what am I saying here? Okay, this should be a maximum here. Okay. I mean, I haven't really explained how this is going to work, but let me give you the rough idea is as follows. So here's a way, if I have a maximum of random variables, of a finite number of random variables, right? There's one way I can find the probability that this maximum is larger than lambda. Well, there's an obvious way which always works, and sometimes I'm not sharp, but it's always there. So what's the probability that the maximum of x1, x2, x3, x4 up to xn is larger than lambda? So it's at most the probability that x1 is larger than lambda, plus the probability that x2 is larger than lambda, plus the probability that x3 is larger than lambda, and you sum all the way up to xn. This is the union bound, right? It's just saying, oh, the event maximum larger than lambda is a union of events. And you bound the probability of the union by the sum of the probabilities. That's the union bound. So here we have a random variable which is a maximum, but you can't really apply this method because you're taking a maximum over an uncountable set. Right? This set is infinite. It's even worse, it's uncountable. So there's no way that you can add probabilities and get a bound on this. So before we apply this union bound idea, we need to first replace the sphere by a smaller set. We lose something when we do that, but what we lose is somehow contained in this. We move from lambda to lambda over 2. And then we need to figure out which lambda makes this small, and then that's going to be the end of the proof. Right, so how does that work? We need to explain this better. So in our case, we're going to use a discrete subset of the sphere instead of the whole sphere in order to do a proof. And we want a nice discrete subset of the sphere. What we want is that any vector in the on the sphere can be well approximated by a vector in this finite set. So the first thing we need is a definition. An epsilon net for a certain subset of Rn is a set that I'm going to call N such that for all S belonging to S, there exists a V belonging to N. Well, here we want N to be contained in S, right? Such that the distance between V and S is less than or equal to epsilon. So this set N has a property that any point in S can be well approximated by an element of it. And let me argue the following. So for proposition, for any symmetric matrix A belonging to n, right, n by n matrix, you have that the operator norm of A is less than 1 minus 2 epsilon maximum over V belonging to N of V transpose A V, inner product A V, where N is an epsilon net for the sphere. And this is for epsilon less than 1/2. Otherwise, you this, right? Epsilon greater than 0. So let's see if we can make sense of this. The operator norm is a maximum like this one. We're over all vectors in the sphere. I want to replace the sphere by a smaller subset, a finite subset. I mean, I still haven't showed you that I can find a finite epsilon net, but that's going to be easy. Right? So I want to say, what's the cost of replacing the sphere by an epsilon net? And the cost is this extra factor that you have here, which you can make arbitrarily close to 1, right, if you take epsilon small. So what's the proof of the proposition? I mean, in this case, it's really simple. This sort of argument is extremely general. So, but in this case, it happens to be very simple. So we know that there exists a V0 belonging to Sn minus 1, such that V0 a V0 is exactly the operator norm. Right? This is a property of symmetric matrices. And take V belonging to the epsilon net such that V minus V0 we will use that for any two vectors A and B in Rn, then you have this bound. Right? So the operator norm is just the maximum norm of this vector, A times B, when B has norm 1, or is the maximum of A times B divided by the norm of B. And how do you achieve the maximum? Well, you multiply by, you take the inner product with another vector, you use Cauchy-Schwarz, and you get this. Right? So this is not hard. So this is 1. And then you get this thing here. So you have that the operator norm of A equals V0 A V0, which equals V A V plus V0 minus V A V0, oh sorry, V plus V0 A V0 minus V, right? It's just, I just need to figure out that if I add these two, I get V0 inner product AV, and then I sum this, I get V0 inner product V0, AV0. And now I'm going to use a triangle inequality. We get VAV plus V0 minus VAV plus V0A V0 minus V. And now I'm going to use this inequality here twice, right? So the first term is less than the sup for V in the epsilon net of V inner product AV. Now, this thing here is upper bounded by the norm times the operator norm times the norm of V. And the same thing here. Right? Just using this inequality twice. And now let's see, right? So this is less than epsilon, because we chose V to be close to V0. This is also less than epsilon. This is less than 1 because V belongs to the net, which is it's contained in the sphere, right? I said that an epsilon net for a set is always contained in that set. And this is also less than equal to 1 because V0 is in the sphere. So what do we get from all of this? We get that the operator norm is less than the supremum plus epsilon times the operator norm plus epsilon times the operator norm. So you get 2 epsilon times the operator norm of A. And now we're done, right? So this is the same as the thing we claimed. We just moved this to the other side and divide. So again, this is a very general kind of argument that sometimes you have a maximum of an infinite, maybe uncountably infinite number of things, and you can replace it by the maximum over a finite family somehow. So there are 2 things we need to do now. First of all, we need to know the size of the epsilon net that we're able to find here, because that will come out eventually, right? So we're going to use a bound of this form. And but also we want to we also need a bound on the probability, on this sort of probability, and that we'll see that there are different ways to get this, but we'll get to that later. So what I want to prove now is just that their epsilon nets are not that big. Well, they're big, but they're within what we accept as reasonable. So proposition, there exists, well, for all epsilon between 0 and 1, there exists an epsilon net for the sphere with elements. Right, so how large do you need an epsilon net to be? Well, it's it's not hard to show that in... Yeah, 2 is divided by epsilon. So, but really, I mean, the thing that matters for us the most is the end here. In the end, it only matters that this is a constant when you fix epsilon and you raise this to the end. So what we need is, as you're going to see, I mean, I was saying something before, I forgot. But anyway, this n here is very important for us. The fact that this grows exponentially with n, but not any faster, it's really what makes this argument work. As we're going to see, this n here will give us a square root of n when we finally solve the problem. And remember that the right order for the operator norm is square root of n. We said this actually should be twice the square root of n, but we already said that we don't care about the sharpest possible result, so we're going to get something of the order of square root of n. And this is essentially related to the exponent here. Right, so how do we find this epsilon n? Well, the proof is very classical, and you can find it in many, many different places. And the idea is we're going to try to build a well-separated set of points. Well, first you choose some x1 that belongs to Sn minus 1. And given x1, xn minus 1, you choose some xm such that the distance, no, okay, let me put it like this. So the balls of radius epsilon over 2 around these m points are disjoint. But then you have to stop if not possible. Let me clarify what this means. Right, so what were we doing here? Okay, let me erase this right away. So this is some sort of algorithm for finding a large set of points which we want to be an epsilon net. And we want this epsilon net to have this, at most this size. So, and here's what the algorithm looks like. I'm going to do it for the one-dimensional sphere, which is, of course, a circle. And even that is hard to draw for me. Right? So we start by choosing one point here. And you look at the ball of radius epsilon over 2 around it. Then you want to choose the second point so that the two balls do not intersect. And then you choose a third point. And then you choose a fourth point. And then you choose a fifth point. And you keep on going, except that at some point you have to stop. Right? Well, we may have to stop. We still don't know that we will stop. And here's what I'm saying. I'm saying, well, if possible, choose another point so that the balls of radius epsilon over 2 do not intersect. But if that's not possible, you just stop there. Right? So the first thing we want to know about this is just like in this drawing, the procedure will stop after a finite number of steps. Let's say after, well, the stop before, let's see, this will stop at m equals m max, which is less than 1 plus 2. Right. And why is it true? Well, proof of A. Well, the idea is this. Suppose that you're able to go all the way up to step m, right? And you carry the procedure up to this step. Suppose we reach a set like this. Then we have the following. So, and here we're going to use kind of a volume estimate to bound the number, to bound the size of m. So on the one hand, by construction, this is the disjoint union, right? Because, again, I'm picking points so that the balls are disjoint. That's how I do things. So if I'm able to take this as far as m steps, I'll have its joint union. So I can compute the volume of this union. I just mean Lebesgue measure if you want. Though you can even talk about volume in this case, in the sense of it's a Jordan measurable set if you care. So this volume is the sum of volumes. And what's the volume of a ball in Rn? Well, up to scaling factor is the same as the volume of a ball centered at 0 with radius 1, right? So here I have m. So there's going to be m times the volume of the ball, sorry, the standard ball, times epsilon over 2 raised to n. I mean, there's a formula for this, but I don't care about what it is. I'm just using the fact that if you take a ball of radius r, its volume is r to the n times the volume of the ball of radius 1. Right. On the other hand, these balls here are always contained in the ball of radius 1 plus epsilon over 2 because well, here I should have been more explicit, but you're always picking points on the sphere, right? And so because the norm of each xy is less than or equal to 1, these are points that are within distance, epsilon over 2, from a guy with norm 1. So everybody in this ball has norm at most 1 plus epsilon over 2, and actually strictly smaller. Right? So, and from this you get that the volume of the union is less than the volume of this ball centered at 0, which is, again, by the same formula, right? You take a ball of radius 1 and multiply this by the radius of the ball. Now you have two inequalities for the, well, you have an equality and an inequality. So you have that this thing here is less than that. Right? So what this is telling is that m times this, which, well, so, okay, m is less than, well, the radius, the ratio of this n divided by epsilon over 2 to the n, which is exactly n here. Right? So what this is telling you is that this procedure will stop, because if we can reach a set, it's only because we can deduce that it has at most a certain number of elements. So if you ever try to get a bigger size, we will not be able to. This must stop. And then part B is just to show that this set is an epsilon net. Right? So why is this? Let me maybe put this over here. So before part B. So the final set is an epsilon net. Why is this? Well, you're adding points, right? At some point you have to stop. This is what it means. It means that if you take any other point, there will be at least one ball that intersects, right? Because well, you've added balls that do not intersect. So if adding an extra point it's not possible, it's because this point has a ball that intersects the previous one. So there's some xi such that the two balls intersect. And what does it mean, right? So it means that, so maybe this is explained in more detail in the notes. But okay, so proof of B. If you stop with x1 and xn, you deduce that for all y in the sphere, there must exist an xi such that the two balls intersect. Otherwise, you could add this y and keep going. Right? Well, what does this mean? If you have two balls that intersect, it's because there is a point that's within distance epsilon over 2 from xi, and also within distance epsilon over 2 from y. Right? So if you take a point P in here, you have that the distance between xi and y is less than the distance from xy to P plus the distance from y to P, and this is less than epsilon. So what this is telling you is that because you have stop, because you have this maximal subset of points with disjoint balls, then any other point on the sphere must be within distance epsilon from one of the points in the set, which means that this is an epsilon net, right? For any point in the sphere, you find a point within distance epsilon. So this is a very classical kind of argument. It's a very good thing to know because, well, I mean, in other contexts it's more complicated, but this idea that somehow, I mean, the basic idea really is that if the concept of an epsilon net makes sense in any metric space. Right? And this greedy procedure, where you get disjoint balls, if it stops, it always gives you an epsilon net. It's not guaranteed to stop because we know we have, for instance, metric spaces with infinite diameter, so you can fit infinitely many balls in there. But if it stops, it's because you have an epsilon net. And the reasoning is this. The two balls intersect, and it's because the 2 points are within distance epsilon. And then you need some criterion to prove that it stops, and usually the criterion you use is some sort of measure estimate. I mean, because if you have a measure on the space, you can try to apply the same reason. I mean, it doesn't always work so nicely, but it can be just any measure. But if you have some measure, you can try to use it. Right, so we're almost running out of time, so I think I'll leave the proof of, how we actually combine these steps for next class. But let me just say one thing that you're going to use so you can think about it when you, before tomorrow. So what is nice about Wigner matrices, and I mean Wigner matrices with Gaussian entries, right? So not a Wigner type matrices, but Wigner matrices with IID Gaussian entries, is that V inner product with Wn V is always a normal random variable with a mean 0 and some variance sigma squared, which you have to compute. Why is this good, right? Well, it's good because in the end, we need bounds for any fixed v, how this behaves. And the way you're going to get those bounds is just by saying, well, for each v, I know I have a Gaussian random variable. And why is this, right? You just need to realize that this is a sum of things like vi, vj times nij, which is the ijth entry of the Wigner matrix. Some terms will appear twice, right, just because nij equals nji. But in the end, you have a sum of independent Gaussians with coefficients. And all you need to do is to compute the variance. You know right away that's, because it's a linear combination of Gaussians with mean 0, it's a Gaussian with mean 0, all you need to do is compute the variance. And once you know that, then you can use everything we know about Gaussians to bound the probabilities here individually. And then we'll be able to give a bound for this thing. But that's on Wednesday. So thank you very much.